All right, so what about the derivative of log base a of x? All right, you know that what the derivative of ln of x, that's log base e, but what if you had something like log base 3 of x or log base 4 of x? All right, so what you have for that is a change of base formula. So hopefully you remember this from your pre-calculus and your algebra 2. You can always change the base by using this formula. Log base anything is equal to, you can use a different base and then just divide by the log of the base. So log base a of x is ln of x over ln of a. Of course, we could say log base 7 and it would still be the same. All right, so anyway, you can in fact use this change of base formula and say, all right, if I had log base a of x, I don't have to learn a new formula, just use change of base formula and then do the derivative from there. But essentially the log base a formula allows you to not have to remember the change of base formula, but you should remember that anyway. All right, anyway, so the derivative of log base a is equal to the derivative of, so I'm going to take this ln x over ln a, and I'm going to rewrite it as 1 over ln a times ln x. All right, that's right, same thing. Now the other thing you got to remember is that the 1 over ln a, that's just a constant, so I can just bring it down when I do the derivative. So I'm going to do the derivative now, it's no longer a derivative. And then the derivative of ln x, we all know is 1 over x. So usually we put that together as 1 over x ln a, and that is what you have here as your formula for log base a of x. So what can I do with that? The derivative of log base 2 of x is equal to 1 over x ln 2, right? What's the derivative of log x? What if I don't write a base? What's the derivative of just log x? Yes, log by itself is always log base 10, called the common log. So if log is not written, if a base is not written, it's base 10. So this is 1 over x ln 10. Is ln 10 equal to 1? No, the common log of 10 is equal to 1. ln of e is equal to 1, but ln of 10 is just some irrational number. All right, so there's how you use that formula. Now look, the idea here is this. You can find now the derivatives of a ton of different kinds of functions, all the way up to here. We have not done these yet, so you can find all those derivatives. You can also find derivatives of those functions in various types of combinations. So the idea is you can find the derivative of like almost any kind of function. And the whole goal of like understanding derivatives is to be able to do the derivative of any function. We like to do that because functions describe things happening in the world, and then the derivative describes the rate of change, and we like to know how fast things in the world are changing because that's important to a lot of things. All right. Now, you know so many of these different things that we're ready to do a quiz on them. So how we're going to do that is this video theoretically should be airing Friday, October 30th. It's all very confusing to me. I'm actually recording this the Saturday before. So time is like a mess for me. But I believe this is going to air Friday, October 30th. And then what I'm going to do is I'll post some reviews. I'll incorporate some review into our lectures for next week. And then I'm going to drop the quiz on Friday, November 6th. That's when the quiz is going to drop. Okay, we'll have some reviews. Well, actually, let's see. See, it's so confusing now because they're going to go to this A-B thing. So what's going to happen is that Tuesday is going to be a B, the next A day next week. Next week, Tuesday is going to be an A day. Except you have Tuesday off next week. So I guess you end up having class on Friday anyway. I think we're going to have this, well, whatever. Whether it's Thursday or Friday, end of the week, next week, the quiz is going to drop. And I'll incorporate some review into our work throughout the week. Okay, but for now, I don't want you to think about the quiz yet. We'll have time to go over it next week and discuss what kind of things are going to be on it. For now, I want to really focus on the chain rule, okay? So the chain rule is something that's like, it's a pretty straightforward concept, but you have to really see it a lot of times before you can really grasp it. So that's why we have some homework assignments to practice, and I'm going to go through all the evens of these homework assignments. So I have Rogowski page, I think it's 175. Notes all over the place here. Yeah, Rogowski page 175. All right, hopefully posted on the Google Classroom by Friday when this airs. All right, so here it is. Here's Rogowski. I'm going to do the evens. You're going to do the odds, okay? So I'm going to start with these evens. So I'm going to start with number 30. So number 30 says y equals sine squared x. So the first thing I want to do is remember that that means sine of x squared. So then I'm going to do y prime. So I'm going to carefully distinguish that I have y and then I have y prime. To do my derivative y prime, we're going to do derivative of the outside function by doing power rule. We're going to keep the inside function the same. Okay, keeping the inside function the same. And then, all right, so technically this is to the first power because we're dropping this exponent 1. All right, and then we're going to go times the derivative of the inside function, so times g prime. That inside function sine, so the derivative is cosine. All right, so if I rewrite that nicely, it's 2 sine x cosine x. Hey, that's the same result when we did it using the product rule, right? Okay, notational comment. So when I'm doing when I'm using this notation, we can say things like derivative of a to the x, derivative of e to the x ln a, and then just drop the derivative sign. So these two functions, here I haven't done any calculus because I haven't done the derivative yet. When I do the derivative, I drop the dx, right? I'm saying the derivative of this is this, okay? When we're using the y and y prime notation, or we could use dy dx, it's important to say, all right, I have y and any manipulations I do of y before I do the derivative, and then I have the derivative, and then any simplifications I do the derivative. But I'm clearly indicating that all these functions are y, all these functions are y prime. Don't put like equals this equals 2 sine x cosine x, okay? This function does not equal 2 sine x cosine x. The derivative of the function equals 2 sine x cosine x. So be careful what you're writing, all right? So number 32 says I have y equals t squared plus 3t plus 1. Whoops, plus 1 to the negative 5/2 power. All right, so first we're going to do let's say that we're doing a derivative. Look for any manipulations. Is there any way we could simplify this? No, there's no way. Like, I wish I could like if this was just the second power, I might consider just squaring out the binomial. It might be easier. Not with 3 terms probably though. So there's no really way to simplify it. So I'm going to use power rule. I'm going to bring that negative 5/2 out to the front. I'm going to drop it 1. I'm going to keep everything inside the same. Right, keeping everything inside the same. And when I drop that exponent 1, it becomes a negative 7/2. And then I just multiply times the derivative of the inside function. I got g prime. Yeah, it's going to be 2t plus 3. 2t plus 3. All right? Okay, squeeze one more in there. Yeah, I'm going to jump down to number 36. We'll come back to 34. I just want to do number 36 because it's got a little bit of weirdness to it. So I have y equals cosine cubed of 12 theta. So the first thing I'm going to do is say that cosine cubed really means that I have cosine of 12 theta cubed. So there are really 3 functions here: cubed, cosine, and 12 theta. It is funcception. It is a funcducken. Many functions stuffed inside each other. All right, but we can still do that. We can still do y prime by starting with the derivative of the most outside function, which is the power. All right, so I'm going to have 3 cosine of 12 theta squared, right? Applying power rule, dropping the exponent 1, bringing the exponent out front. And then I have to go times the derivative of the inside function, but the inside function has its own inside function. So I'm going to do the derivative of the outside inside function. That's this one. Derivative of cosine is negative sine. So when you write the negative sign, make sure you don't do this. Just write negative because it looks like a minus sign. I have to put a parentheses to indicate I'm multiplying by negative sign. And I'm going to keep the inside function the same, 12 theta. All right. So now I'm keeping this inside function the same. And then I have to do times another derivative, let's call it h prime. All right, and so the derivative of 12 theta is 12. So if I have a function within a function within a function, I can just apply the chain rule multiple times. Power rule, derivative of cosine is negative sine, keep the 12 theta the same, and then derivative of 12 theta. More examples coming up.